Math 2414, improper integrals. Discontinuous integrands, example 1. We've got 3 examples and that'll wrap up this series. Let's integrate 1 over the square root of x minus 2 dx from 2 to 5. Notice any problems with the integrand and the limits of integration? Well, if you have a denominator, you have to be cognizant of when it could be 0. And when is this denominator equal to 0? When x is equal to 2. Notice, 1 over the square root of x minus 2 is discontinuous at x equals 2. It makes the denominator 0. And by the way, making a denominator 0 doesn't make you have a vertical asymptote. It's when your denominator is 0 and your numerator isn't. Or if it makes both of them equal to 0, then you factor, cancel, and try again. But if a number makes the bottom equal to 0 but not the top, then you get a vertical asymptote. So how do we attack this? Well, same way as before. You identify the problem, in this case it's 2, replace it with a variable, so the integral from t to 5, and then you integrate this thing. Let's go ahead and prepare it for integration. We don't integrate radicals, we integrate powers. So we're going to rewrite the square root as a 1/2 power, but being in a denominator, we'll move it upstairs and make it a negative 1/2 power. You have to be fluid in making this algebraic change in preparation for the integration. All right, technically we would do a substitution, but if we said u equals x minus 2, then du would be dx, and anytime you're doing a substitution, du equals dx, stop the substitution. There's no need to do it, just do the rule. There's no chain rule to undo. All right, so the rule would say add 1 to the exponent, negative 1/2 plus 1 is 1/2. Multiply by the reciprocal, or the reciprocal of 1/2 is 2, and this is going from t to 5. All right, let's restore the 1/2 back to a square root while we're evaluating. Substitute 5 for the x, minus substitute t for the x. We can clean this up just a little bit. We can say 5 minus 2 is the square root of, square root of 5 minus 2 is the square root of 3, but that's really as far as we can push that antiderivative. Okay? Then, take the limit. But when you take this limit, technically you need to be careful, because I'm not just approaching 2. I'm approaching 2 from the right. How do I know that? I'm integrating over the interval 2 to 5. This was the problem. I replaced it with a t, but it has to be inside this interval. And now we push that over towards the 2. So it's coming in from the right side of 2. Of that guy. 2 squared to 3 minus 2 squared to t minus 2. And from a technical perspective, going back to the coming in from the right, if this wasn't here, a limit that approaches a number without mentioning left or right is asking 3 questions. Where's it coming in from the right? Where's it coming in from the left? And do they meet at the same place? This limit doesn't exist because you can't come in from the left side of 2, because if you came in from the left side of 2, you would be less than 2, and if you're less than 2, and I put you here, you become negative, we're square rooting negatives, bad. You can do calculus with complex numbers, just not at this level. All right, so we are coming in from the right, which is good. And basic limit strategy is plug in the number and hope nothing goes bad. Well, at this point we can. At this point we can substitute the 2 for the t, because when we do, this becomes the square root of 0, which is just 0. So this becomes 2 square root of 3 minus 0. It's over. The graph of this would look something like, let's see, it would start at 2. It would have a vertical asymptote, and it would only exist on the right side, because on the left side, we would get square roots and negatives. So it would have something that looks like that, and we're saying that when we go from 2 to 5, we get a finite area. So this is the same geometric issue we saw earlier with the infinite limits of infinity, but instead, it was like, go forever that way, and now it's like, well, don't go forever left to right, but you're going to go forever up. So we're really addressing the same issue about an unbounded lamina having a possibly finite area, depending upon the particular problem. But as far as the execution of it, I'm not gonna lie to you. If you totally overlooked the 2 and the limit and everything and just flat out did the integral, you would get the same answer. And I'm letting you know that because some of you are going to discover, hey, I don't have to do this limit stuff for the t, I just do the problem. Let me just integrate this into that, stick in 5 and 2, and then get my answer. And you would get the answer because in the end, that's what we actually did. But that doesn't always work. So, plus, that's not how this integral is defined. So if you're in my class, when I'm grading these problems, I will be looking for the steps, not just bypassing steps to get to the answer fast.